Today our lesson will be on hypothesis testing. But before that, we are going to have a review of some basic concepts which you need when we are going to do hypothesis testing. Okay, so we have data and variables. So we have studied that in the descriptive statistics. So when we say data, those are the answers to questions or measurements from the experiment. So if you have survey, what you will get are data. When you do experiment, when you do clinical trials or case control, you will also get data. When you are going to do market research, you will also get data that is needed for your market segmentation. Then we have encountered the term variable. These are measurements which varies between subjects, and examples of that are height and gender. Okay, so these are also some of the variables that we are going to encounter when we collect data. Another example when we do market research is the income. So we are going to look into the income so that we would determine the buying capacity of the residents or the community, so that when we are going to put up our business, we would know how much price are we going to put up on our goods. Then we have the data types. We have the data variables such as scale and categorical. So you will encounter this when you are going to do coding in the SPSS. You have scale, and that refers to numerical measurements, or those are count data, and that is considered in the SPSS as scale. So interval and ratio level variables are considered in SPSS simply as scale. Then categorical. So this appears as categories. Okay, so the tick boxes on the questionnaire, such as when you are going to have your gender, place of residence, quality of goods, that is categorical. And in SPSS, it is labeled, or you're going to classify that as nominal, categorical, and there is ordinal. But basically, the data types that we are going to encounter when we do research are simply scale and categorical, because sometimes the ordinal level variables are considered under categorical. Then we have the data types. Under the scale, we have continuous and discrete, and under categorical, those are ordinal and nominal, as I have mentioned. Okay, so example of nominals, your pets. And ordinal, that is the rank, let's say for example, after a relay, so there are winners, or if there is a marathon, there are winners ranked 1, first, second, and third, so that's ordinal. Then we have discrete, when we are counting the number of students in the class, that is discrete. And continuous, those are results of measurement. Then we also have encountered the term populations and samples. So, sample represents the whole population, as I've mentioned, but when we do research, we will only sample the population. We will get samples so that it's going to represent the whole population, and you know the reasons why. Because sometimes it is impossible to contact everybody in the population, so we sample, and it is costly when we have all members of the population to be studied, so we only have to get a few to respond to our study. And then also there are some tests which are destructive in nature, so we are not going to allow to hurt everybody, and that is not also ethical. So ethically, we are not allowed to harm or endanger everyone in the population. That's why we only have to choose a sample. Okay, and also it is time consuming to contact everybody in the population. That's why we need to sample. Then we encounter the term point estimation. Okay, so the point estimate. So, and the interval estimate, if we also have the interval estimate. So in the point estimation, but we usually have the point estimation when we do hypothesis testing because we only have to observe a sample. Then we are going observe the sample using single values before we are going to generalize it to the whole population. But if it is a survey data, it is important that we are also going to present the interval estimate. Sometimes if in epidemiological studies, if we are talking about public health, we are going to present also the confidence interval so that the consumers would know that at this point we are only 95% confident, and that this value point estimate that we have computed, or as a result of our statistical computation, would lie on that same interval estimate. Okay, so now let's have our lesson on hypothesis testing. Okay, so first is we need to understand the logic of hypothesis testing. Okay, so hypothesis testing's main objective is to make decisions or inferences from sample data based on evidence, and we are going to generalize it to the population. So the sample data used to choose between two choices, that is the hypothesis or statements about the population, and we typically do this by comparing what we have observed to what we expect if one of the statements was true. So if you're going to take a look at this picture, the cat is faced on with a decision whether to go out in the snow and get cold and wet, or stay inside. So the null hypothesis here is for the cat is I won't get my paws wet and cold. And the alternative hypothesis is my paws will get wet and cold. Okay, so how is it going to decide whether to go out or not is um, based on the data that it has collected previously. That is the same way as when we are going to compare hypothesis testing with the logic of the court. The defendant would say, I am not guilty, I am innocent, and the other side would say, you are guilty. So the prosecution is going to present pieces of evidence to convict that person. And if you fail to convict that person, meaning to say, it does not mean to say that that person is not guilty. Only that the prosecution failed to present a lot of evidence that is going to prosecute that defendant. So the hypothesis testing framework, okay, so we could try explaining that in the context of the court case. So members in the jury have to decide whether a person is guilty or innocent based on evidence. So in our case, that's the judge who's going to decide whether the person is guilty or innocent based on the pieces of evidence that the prosecution is going to present. So the null hypothesis is the person is innocent. And the alternative hypothesis is the person is not innocent, the person is not guilty. The null hypothesis is this is the statement of the defendant. And the alternative hypothesis is the statement of the prosecution. They have to prosecute that defendant. So the null can be rejected if there is enough evidence to present a doubt. Okay, so there is a doubt. So you have to present that there is doubt. Okay, so that the jury or the judge can only convict if there is beyond reasonable doubt for the null of innocence. That is why the judge would say beyond reasonable doubt. So there is that phrase beyond reasonable doubt. That is just the same as in the concept of hypothesis testing. And they do not know whether the person is really guilty or innocent, so they sometimes can make a mistake. So there are errors. Okay, so one error here is the type 1. There are two types of error. The one is the type 1 error and the other two is the type 2 error. So this table that I am presenting is the risk table. So there is what you call the false positive and the false negative. Okay, so if you take a look at this one, this is the hypothesis here. This is for the prosecution. This is for the top is for the defendant. So when the prosecution was not able to present enough evidence and the decision of the judge is, yeah, you are really innocent, so that is a correct conclusion. But if the person is innocent and yet the judge convicts it of the crime, even though he is innocent, then that is what you call a type 1 error. And it's because on the side of the defendant, they were not able to present pieces of evidence to claim that the defendant is really innocent. And if that is that error, if you are going to commit that error, so that is a big blunder because you imprison a person who is innocent and the guilty is free. Now, if the null hypothesis is false, there is really relationship, but you accept it, that you accept that there is really no relationship, although there is difference or relationship, then that is a type 2 error. But when it is, when you are going to reject it because it's really false, there is really pieces of evidence that is going to convict that person, that is the correct conclusion. So in this case, if we're referring it to the court case, if that defendant is guilty, but the judge says that person is innocent, then what is the blunder committed is a type 2 error. You release a guilty convict or you release a guilty person. Okay, so the chances of committing these two types of error are inversely proportional. So you have to take note of that. That is, when you are going to decrease your type 1 error, then your chances are you are increasing also your type 2 error and vice versa. That is why you don't have to be very stringent, and that is why the level of significance that you are going to set is always at 0.05. So how does a type 1 error occur? So a type 1 error is also known as the false positive and occurs when a researcher incorrectly rejects a true null hypothesis. So that means that your report and your findings that are significant when in fact they have occurred by chance. So this is the same thing, the false positive means that when you are tested of COVID-19, the result says that you are positive of COVID-19, when in fact you are not positive of COVID-19. The truth is you are negative. And the probability of making a type 1 error is represented by the alpha level. So that is the 0.05 that I said. And if it is for medical studies, it is 0.01. Okay, so which is the p-value below which you reject the null hypothesis. So if a p-value of 0.05 indicates that you are willing to accept a 5% chance that you are wrong when you reject the null hypothesis. So that's, that's the alpha. So when your alpha is 0.05, you are indicating that you are willing to accept a 5% chance that you will get wrong when you reject the null hypothesis. And that is always the case that we are going to base our p-value. So if our p-value is less than the alpha, then we are going to say that there is significant relationship or there is significant difference. And if the p-value is higher than the alpha at 0.05, so it means you get a p-value of 0.056, it's more than 0.05, then you are going to say that there is no no significant relationship. Okay, so now in the type 1, how you can reduce your risk of committing a type 1 error by using a lower value of p. So for example, you have 0.01, that would mean there is a risk that is only 1% chance of committing the error. However, using that lower value of your alpha means that you will be less likely to detect a true difference if one really exists, and thus you are risking a type 2 error. That is the false negative. Okay, so how does a type 2 error occur? So a type 2 error is also known as the false negative. Okay, so that's the one I told you. And occurs when a researcher fails to reject a null hypothesis which is really false. So here, a researcher concludes there is a significant effect when actually there really is. So the probability of making a type 2 error is called your beta. So the type 1 error is the alpha and the type 2 error is the beta, and this is related to the power of the statistical test. This is also called the power of the test. And you can decrease your risk of committing a type 2 error by ensuring your test has enough power. Okay, so why are they important? So, the type 1 and the type 2 errors are important because these are the consequences of making type 1 error mean that changes or interventions are made which are unnecessary, and thus it is a waste of time and resources. So, again, if a type 1 error is committed, so you mean that if there are policy changes, you have changed that policy or the interventions are being changed, okay, but these are not necessary, and that you are wasting the time and the resources, or you are wasting resources in general. And if type 2 error is the type 2 error is committed, type 2 errors typically lead to the preservation of the status quo. Okay, so that is interventions remain the same when change is really needed. So in the type 1 error, you've made interventions, you've made changes, but which are unnecessary, thus wasting time and resources. And when type 2 error is committed, you are telling it's status quo, don't change anything, don't intervene when there is really going to be needed. There is going to be interventions needed, and when there is change that is really going to be needed. Okay, there are steps in undertaking a hypothesis test. First, these are the steps. You have to define your study question, that is your objective. Then from that objective, you state your null and alternative hypothesis. So you will encounter that in your research, how you're going to state your objectives and when are we going to state the alternative and the null hypothesis. And you have to calculate a test statistic, calculate a p-value, but that is the traditional method of hypothesis testing, because when we are going to use statistical softwares, we don't have to calculate the test statistic and the p-value, but it's going to be a part of the results of a statistical software when you run your statistical test, and you make a decision or interpret your conclusions based on that uh, calculation or based on the p-value. So usually we base our decision on the p-value. But the main question here is, how are we going to choose a suitable test? The problem is choosing the suitable test. That is what we are going to learn. And that concept of choosing a suitable test is not learned overnight. It is learned by experience, and it is learned by looking into different objectives in the research problems, okay, or in the research objectives. That is why what we are going to discuss here are some basic statistical tests, but uh, on how you're going to choose it or when are you going to use it, that is really based on your understanding of the objectives of the problem. Let us have our example on the Titanic to illustrate chi-square. Okay, so if you remember, the ship Titanic sank in 1912 with the loss of most of its passengers. So it's one of the biggest mishap in the history of shipping industry. In fact, a majority of its crews and passengers died. So out of the 1,309 crews and passengers aboard that ship, 809 of them died, and that is 61.8%. Okay, now the research question here is, did class of travel affect survival, whether you are traveling first class, second class, or third class? So if you take a look at the variables that we are going to compare here, or we are going to look into its association, we have two variables here, the class of travel and the survival, and they are both categorical. So if both variables are categorical, the class of travel is in categories: first class, second class, third class. And survival is either you died or you survived, or that is the outcome. Okay, so it's also categorical. So that is why we are using the chi-square test. So how do we do it? So the first thing that you are going to do, if you remember the steps of hypothesis testing, you would say that there is no association between class and survival. That is the statement of the null hypothesis. No association between class and survival. And the alternative hypothesis is there is association between class and survival. So take note of the no association in the null, and take note of in the alternative there is an association. So in the alternative, you are negating your the null hypothesis. So we are going to provide sufficient evidence to reject the null hypothesis, and thus we are going to accept the alternative hypothesis that there is really an association between class and survival. Looking at this cross tabulation, this is a snippet of the SPSS output when you run SPSS. Okay, so here you have your class, first class, second class, third class, and you have your That is your rows. And your columns is the outcome, whether you died or the passenger died or survived. And if you take a look at the first class, 323 of the passengers are traveling first class, and mostly of them 200 survived. Okay, and a few died. That's 123 died. On the second class, 277 uh, were traveling second class, and 119 survived. Many died, 158. While on the third class, 709 of them were traveling first class. But if you take a look at the number of those who died, 528 of those 709 died in that incident. So a total of 809, if you add those who died, 809 out of 1,309, and only 500 survived. And this is a 3 by 2 contingency table, 3 rows and 2 columns. The 3 rows, you have your first class, second class, third class, and the column, which is died and survived. Okay, so if we take a look at it on a graph, okay, so what would be expected if the null is true? So same proportion of people would have died in each class. So if you take a look at the blue and the red one, the red are the expected deaths and the blue are the observed deaths. So how are you going to compute for the expected deaths? That is expected deaths, or that is the expected number of those people who died in each class, is the actual proportion 0.618 times the number in that class. So how many are traveling in that class? That is the expected deaths. And if you're going to take a look at chi-squared, okay, so as I mentioned, we want to see if two categorical variables are related, and we are going to use the observed frequency and the expected frequency if we do it manually, and that is the formula. But when we are not doing it manually, we are going to use a statistical software. So using SPSS, you have to take note of this one, although we will run it later on the simulation using the SPSS. Okay, so I will also be posting that later on. I will show you the simulation. Okay, so let's analyze. Everything that you do with the SPSS, you're going to click on the analyze. And then descriptive statistics, you click that, and then cross tabs. So when you click cross tabs, you click on the statistics button and select chi-squared. And after you select chi-squared, you click OK, and you will get the result. Okay, so at the bottom, the SPSS is going to tell you that there are no cells to have expected count less than 5, because if you have an expected count of less than 5, you cannot use the chi-squared test, but instead you are going to use the Fisher's exact test. It's not showing here the Fisher exact test because of this premise that there are no cells which have less than 5 frequency. But if there is less than 5, then Fisher's exact test is going to show in the output. And that Pearson chi-square, the value 127.859, that is the test statistic, or we call that one the computed value. That is the computed value of the chi-square statistic. And the asymptotic significance, two-sided, that's the p-value, that's 0.000, that if you are going to double-click that one, you will get a result of less than 0.001. So what does it mean when you have a result of less than 0.001 as your p-value? That means to say there is, it means a strongly significant association. Okay, so the decision rule. So, hypothesis testing decision rule that is based on the SPSS. Okay, so if you take a look at that one, you will say that if it is less than 0.05, because we always have a default of 0.05, when your p-value is less than 0.05, there is association. There is evidence. But if the p-value is greater than 0.05, there is no association. That means you have to accept the null or fail to reject the null because there is no association. So what you're going to remember is if it is less than the alpha, there is association, there is relationship, there is an effect, or there is difference. And if it is more than your alpha of 0.05, then you will say there is no association, there is no difference, there is no relationship, there is no effect. And if you are going to take a look at the chi-square distribution, okay, so the chi-square distribution is a skewed distribution which varies depending on the degrees of freedom. That is computed as the number of rows minus 1 times the numbers of column minus 1. But then when you run it in the SPSS, you don't need to compute that manually, multiplying the number of rows minus 1 times the number of columns minus 1, because SPSS would always give the result, the DF. If you remember it on the table, there is a column for degrees of freedom, that's DF. Again, so p-value is a very technical term. Okay, so probability, the p-value is the probability of getting a test statistic at least as extreme as the one calculated if the null is true, or the p-value is the probability of committing the type 1 error. That's what we mean by p-value. And in the Titanic example, okay, so we got a p-value of less than 0.001, so there is really strong association. So we would say there is really strong association between class of travel and survival. Okay, so if we take a look at that one, you can have your interpretation. When you are going to report, okay, so that is reporting results of a chi-square. So when you are going to report results of a chi-square, you are going to write this one. This is the APA format of writing reports in statistical results. So if it is a chi-square, so that is x squared. Here, it's using an under subscript 2. Okay, so the subscript 2 can be on other sites. Instead that it's using a subscript 2 for the degree of freedom, that's the degree of freedom, you are going to put it in an open close parenthesis. So x squared open close parenthesis 2 equals 127.86. That's the computed value. And your P is less than 0.001. That is to suggest there is an association between class and survival. And as I have mentioned, there is strong association. Or you would say that class of travel and survival is strongly associated, comma, then you are going to have x squared open close parenthesis 2 equals 127.86 comma p less than 0.001. I would like to reiterate that although this is the I also have found that sometimes the writing of a 0.05 and the 0.001, okay, so in that case we are only emphasizing that it is there is a decimal point after it, but then some authors would not want to put up 0 before the decimal point because we are not comparing it to a whole number. Okay, so we just have to be consistent that although there are authors who are using this one, in most cases they are using as putting a zero before the decimal point, but I would like to have an advocacy of removing that zero. Okay, so but what is the nature of this association of relationships? So how are we going to determine the nature of association of this relationship? Is we're going to make a table, I mean a graph. Okay, so you have the contingency table. Look at those who died and look at those who survived. Okay, so take note of the percentage. You have 38 and roughly 62 survived in the first class. You have 57 died in the second class and 43% 57% died in the second class and 43% survived. And in the third class, you have 74.5 or roughly 75% or just 74%, and this is 26%. So if you're going to take a look at it on a table, put it in a stack bar showing the illustration of the relationship, so you have it there. Notice that as you move down the line, okay, chances are you're going to die. So many of those who died are in the third class, while those who survived are mainly coming from the first class. So what can be the implication to this one? Implication to this one is those who are in the third class are at the bottom of the ship. So when they're going up for the survival kits or survival equipment, there is already a stampede. Okay, so some maybe were not able to go up because of the stampede at the bottom, while those who are in the first class, they are rich people, they are known personalities, and they are on the top of the ship, so it's near for them to get the survival equipment, plus they are being helped by the crew because they are known personalities. What if there are low expected cell counts with the chi-squared test? Okay, so in the problem of the Titanic, there are no low expected cell counts, because if you notice, it's those who died, you have 200, 171, 438, and those who survived, 123, 106, 271, and you have 323 total, 277 and 709. So there are 0 cells with low expected counts less than 5%. So if there are cells which have low expected cell counts, okay, what you are going to do, or what the SPSS would give you, is the Fisher's exact test. So the low cell counts with the chi-squared test, okay, so you have expected counts less than 5, and the SPSS reports it also. If more than 20%, then the test statistic does not approximate a chi-square distribution very well. That's why it's going to use the Fisher's exact test. So in that case, when it's run the chi-squared, it's not showing the Fisher's exact test because of the premise that there is none which is having a low cell count. And in larger tables, 3 by 2 tables, sometimes you have to collapse. So if it is some columns are having a less than 5 cell counts, you have to collapse. So collapsing means you have to combine. Okay, so combine categories to make cell counts larger, provided that it is also meaningful.